Welcome back to another episode of Mr. McCune's Minute Science. Today we're going to learn how to balance chemical equations. Now, why would we need to learn how to balance chemical equations? Well, there's something that we need to look at. First, we need an example equation. Here I have magnesium plus oxygen yields magnesium oxide. When we look at that in its actual chemical formulas, we can see that as Mg plus O2 yields MgO. Balancing. Well, that's where we need to start this video. So there are two types of chemical reactions. There's going to be a balanced chemical reaction, which means there is an equal number of atoms on the left side, or the reactant side, as there will be on the right side, or the product side. An unbalanced reaction is exactly what you would think it would be. There is an unequal representation of magnesium on the left side in comparison to it on the right side of the equation. So the reason this is so important, and the reason we have to balance equations, is because there's something called the law of conservation of mass, meaning we can't just eliminate or delete magnesium or matter through a reaction. There has to be the equal amount coming out on the other side. As it goes through this change, or this reaction at the yield arrow, we need to have the exact same amount of mass in these atoms on the left side as we do on the right side. Nothing can change that. So we have to go in and we have to manipulate things called coefficients to make that happen. So the first thing we're going to need to do is get out our example. So we have Mg plus O2 yields MgO. I want to be able to first, and I'm going to put down steps and rules here in the top right, and I'm going to leave those on the screen for the rest of this video. So now I have Mg plus O2 yields MgO. Step 1 is going to be list the atoms on the reactants and products. Easy enough. So I have my arrow down the middle. On the left side I have a magnesium and I have oxygens. On the right side I also have magnesium and oxygen. That's exactly what I needed. Good. The second step is to record the number of atoms that you currently have. There's currently one magnesium and two oxygens. In the products, there's one magnesium and one oxygen. The magnesiums look great. There's both one on the reactants and the products, so there's nothing that we have to do necessarily to that initially. But when I look at the oxygens, I notice that there is twice as many on the reactants. That's not going to work. It's unbalanced. So now I need to figure out a way to get the oxygens on the products to match the oxygens on the reactants. Well, I look through at step 3 and it says add coefficients as whole numbers to elements or compounds in order to balance them. So I want 2 oxygens, so I'll use a coefficient of 2 in front of the magnesium oxide to give me this 2 oxygens. Instead of having 1 now, I have 2. What ended up happening in response, though, was because I had to add the coefficient in front of the entire compound, I am not allowed to just insert a 2 in front of, or break up a compound to put the 2 in front of the oxygen. I had to place it in front of the compound. You'll always have to do that. That is a critical rule. Because I did that, I didn't just give myself 2 oxygens, I gave myself 2 MgOs, which means instead of 1 magnesium on my products, I now have 2. Well, we made our oxygens really happy on both sides, but we now have created a problem with our magnesiums. We can simply fix this problem by going back and using a whole number coefficient of 2 in front of the Mg. Now, I have 2 Mg plus O2 yields 2 MgO. Everything is matching up. We have an equal number of atoms on the left side as we do on our right side. The other rules that we need to be paying attention to is that we can't change subscripts. So this O2, this subscript 2, cannot be changed. That is an integral part of the reaction that we don't get to manipulate. We also have to make sure that we are only using whole number coefficients. We can't use 2.5, we can't use fractions or decimals. And lastly, always use the most reduced form of coefficients that you can. Our next example, and we've seen this example because we watched this reaction in the test tubes in my kitchen in our types of reactions experiments. This would have been our single replacement reaction with copper and silver nitrate. Now let's balance. So I always want to start with step one where I list the atoms that I have. I have copper, I have silver, and we know that a polyatomic ion comes as a package, so we don't just have NO3, we have nitrates. So we have NO3. It's not a separate nitrogen and oxygen that we're looking for. We're looking for the entire bundle or package of NO3. On our right side, we also had copper, silver, and nitrate. The next step is to list how many of each of these atoms that we have. We have one copper on the reactants, one silver, and one nitrate. On our products, we had one copper, one silver, and we had 2 nitrates. Well, we have a disparity here between our nitrates, so we have to make the reactants match the products. So we're going to add a coefficient in front of the entire compound. Again, we can't just insert it in between. So now we have fixed our nitrate problem. Now we have 2 nitrates, but because there's a 2 in front of the Ag, we also now have 2 silvers. That created a problem here, so we have to take another coefficient to fix that problem and add a 2 in front of the silver on the products. Now, I am completely balanced. If you're starting to get the hang of this, you can notice it's a lot like solving a puzzle. You get to be kind of creative. There's no perfect way of doing this. There's no cookie cutter mold, but you have to play with the numbers and see some different patterns. And the more you do, the better you'll get at seeing those. Golden rain from the last video. This would have been our lead nitrate and potassium iodide double replacement reaction. Now, we want to do the exact same processes we've been doing this entire time. We want to list the things that we have. On our reactants, we have 1 lead, 2 nitrates, because there's a subscript 2 on the nitrate, and 2 iodides. So now we have 2 things that are problems. We have a disparity between the nitrates and the iodides. Where you want to start is fine wherever you want to go. So I'm going to start focusing on my nitrates because they're at the top of my list. So I know I need to have 2 on my product side, so I will add a coefficient of 2 in front of the KNO3. That fixes my problem with nitrates. However, it creates a new problem because I have 2 potassiums. I can go over into this section and I can now add a coefficient of 2 in front of the potassium iodide because I wanted to match up my potassiums. I fixed that, but I gave myself 2 iodides. Was that a problem? No, because I ended up needing the second iodide anyways to balance my equation. So just by adding these 2 2's as coefficients, I successfully balanced a really complicated looking double replacement reaction. A lot of letters, a lot of numbers, but we were able to break it down pretty easily. That's most of the problem that you're going to deal with in C, especially at this level of chemistry that you're at. Let's take a look at a combustion reaction, because combustion reactions are where it can get a lot more interesting, where we have much bigger coefficients that we have to mess with. Just like we were doing, we're back to one of the examples that we used in our last video. This was octane, a chemical found in gasoline, burning with oxygen to create carbon dioxide and water as products. Same process. And this is where you have to pay attention. I don't just have 2 oxygens because there's 2 with carbon dioxide and there's 1 with water. So I actually have 3 oxygens. So when you're doing combustion reactions, my biggest suggestion and biggest hint is to leave the O2 for last. Let that be the last thing you try to solve. Try to solve the other atoms first and then get to your oxygens, because typically in a combustion reaction, this coefficient that needs to be put in front of an oxygen sometimes can be really large. I want to start with the carbons. So I have 8 carbons on my left, I need 8 on my right, so why not throw a coefficient of 8 in front of the CO2? That gives me 8 carbons, but what else else it does is it gives me 16 oxygens, 17 oxygens now. So I have 17 oxygens. I'm going to leave oxygens for last still, so I'm going to go to my hydrogens. I have 18. I want to have 18 over here. There's already an H2. In order to get 18 of them, I'd add a coefficient of 9. 9 times 2 gives me the 18 I was looking for. Correction, I meant to put this down here. My oxygens are 17. Now my hydrogens are 18. So I have good with carbon, good with my hydrogens. However, my oxygens are still kind of messed up. And when we put the 9 in front of the H2O, it also changed our oxygens from 17 to a different number now. 9 plus the 16 we already had, we have 25 oxygens. The problem here is rule number 2 says coefficients must always be whole numbers, because it seems like it would be easy for me to come through here and place a 12.5 in front of the O2. The problem with that is I can't use a decimal. One thing that I know from math class is that anytime you have an odd number, if you multiply it by 2, you'll get an even number. So something that people typically do in combustion reactions is multiply their entire equation or coefficients by 2. So I'll take each compound and multiply it by 2. I have C8H18, there's no coefficient there. If there's no coefficient, that really means there's a 1. If I take 1 times 2, I'll get 2. So there's my 2. I'm going to go through and double everything and then count everything up. 12.5 times 2 is going to be 25. 8 times 2, 16. 9 times 2 is 18. I'm going to write this in a little cleaner format directly on my page. Let's go through and count our atoms. We doubled the coefficients that we had prior. Now I have 16 carbons. I have 36 hydrogens, and I have 50 oxygens. On my product side, I have 16 carbons. That's looking pretty good. I have 16 times 2 oxygens will be 32. So I have 32. I'm looking at H2O now. I have 18 times the 2 hydrogens, gives me 36 hydrogens. That's good. And I also had the 18 oxygens for that compound. So I had 32 plus 18, that equals 50 oxygens. So this was a much more complicated example, but by using these coefficients, we were able to get everything to match up in its most reduced possible form. And we were able to accomplish that by multiplying by 2 when we had that odd number of oxygens. Again, you're going to have to play with those ones. I promise you that the combustion ones are going to be the most challenging for you, but it's almost like solving a puzzle. I think you'll enjoy doing them. The other ones are a little bit more straightforward. Hope you guys enjoy. There is a practice sheet. It's actually the exact same reactions that you used for our last practice sheet, but this time we're going to balance all of those chemical reactions. See ya.